needle on the speedometer had nowhere left to go. It sat frozen at 120 miles per hour. Not because the locomotive had reached its limit, but because the gauge itself could not register anything beyond that point. The person at the throttle could feel it, hear it, sense it through the frame and rails that this machine was moving far faster than anyone had planned to admit. Somewhere between Ohio and Indiana in the mid-1940s, a train built to redefine American speed was quietly crossing into territory no steam locomotive was ever meant to survive, and the consequences of that moment would echo long after every example of the engine was gone. The stretch of railroad between Crestline, Ohio, and Fort Wayne, Indiana, had become an unlikely proving ground. Over the course of an entire month, a technician from Franklin Railway Supply rode these trains in secrecy, counting mileposts with a stopwatch. He was not officially assigned to the railroad. His presence was not documented in Pennsylvania railroad records. According to accounts that surfaced decades later through interviews with Franklin engineers, his mission was simple and deeply unsettling. Find out why the valve gear kept failing. The numbers he reportedly recorded were alarming. These trains were not running at 110 or even 120 miles per hour. They were being pushed well past 130 to recover lost time, and on at least one run, the timing suggested a sustained speed of 142 miles per hour across several miles of track. Other later claims suggested that with lighter consists of 6 or 7 cars, similar speeds may have been reached more than once. Those figures have never been officially verified, and no Pennsylvania Railroad dynamometer car recorded such runs, but the pattern of mechanical failure told its own story. Franklin's Type A poppet valves were guaranteed for continuous operation at 100 miles per hour, with brief excursions up to 125. Above that range, failures became frequent and unpredictable. Extensive testing followed, using different materials and revised designs, yet the conclusion remained the same. Above roughly 130 miles per hour, the valves could not survive reliably. It did not matter how carefully they were built. The forces involved were simply too violent. The unsettling part was that the engineers running these trains could not see how fast they were going. The speedometer stopped at 120, leaving everything beyond that to instinct and experience. When the needle pinned itself, the illusion of control remained, even as the locomotive crossed into a range where the machinery began tearing itself apart. According to later recollections, Julius Kirchhoff at Franklin received repeated reports of failures along that same Indiana and Ohio corridor. Rather than confronting the Pennsylvania Railroad directly, Franklin focused on trying to make the valves stronger, quietly chasing a solution to a problem rooted in speed no one wanted to officially acknowledge. To understand why the Pennsylvania Railroad was willing to tolerate this risk, it helps to understand the crisis it faced by 1940. The railroad's pride, the K4 Pacific, had been the backbone of its passenger service for decades. 425 of them had been built between 1914 and 1928, and for years they symbolized power and prestige. By the late 1930s, they could no longer keep up. Passenger trains were heavier, schedules tighter, and competition fiercer. On many routes, 2 K4s were coupled together to pull a single train, requiring 2 crews and doubling operating costs. The financial strain was severe. Rival railroads were moving ahead. The New York Central fielded its Hudsons, fast and capable, while other major lines adopted massive northern types with 4-wheel leading trucks and 4-wheel trailing trucks. Compared to these machines, Pennsylvania's steam fleet looked increasingly outdated. Baldwin Locomotive Works offered a bold solution. Instead of one set of driving wheels, split them into 2. Each set would have its own cylinders and rods, all mounted on a single rigid frame. Smaller cylinders meant lighter reciprocating parts, reduced hammer blow on the rails, and the promise of unprecedented speed. On paper, the duplex drive looked like the future. The Pennsylvania Railroad committed early. On June 26, 1940, 2 prototypes were ordered at a cost of $600,000, By December 20th, 1944, the board authorized full production. 50 additional locomotives followed between 1945 and 1946. The total bill reached $14,125,000, or $282,500 per locomotive, a figure that translates to roughly $4 billion in today's money for the entire program. This was not an experiment. It was a massive bet on a new kind of steam, power. The flaw in the design was subtle and devastating. The two sets of driving wheels were not mechanically linked to each other. They shared a frame, but nothing enforced perfect synchronization. At speed, if one set began to slip even slightly, the balance collapsed instantly. Power surged unevenly, rods thrashed, and the valve gear absorbed forces it had never been designed to handle. At 80 miles per hour, Trains magazine later described the situation as frightening. At far higher speeds, it became destructive. The problem was made worse by human factors. Engineers who had spent their careers on K4 Pacifics were handed these complex machines with minimal instruction. There was no comprehensive training program for duplex operation. Habits carried over. Throttle movements that were harmless on older locomotives triggered violent wheel slip on the T1. Each slip slammed stress through the poppet valves, accelerating fatigue and failure. Yet the railroad pressed on, placing all 50 production units into service across multiple divisions, often with crews learning the machines while hauling revenue trains. The T1s were astonishing performers. They steamed freely, accelerated hard, and once moving seemed eager to run faster than anything before them. That same eagerness made them dangerous to themselves. Their own power allowed them to exceed their design limits with ease. Repeated valve failures sent locomotives back to the shops again and again, eroding availability. Prototype 6110 had logged 120,000 miles by April 1944. In regular service, some production units accumulated more than 8,000 miles per month. The mileage was impressive, but the downtime was crippling. Maintenance was another enemy. The Franklin valve gear on the front engine sat hidden behind sleek streamlining. On the rear engine, it was squeezed tightly between the cylinders. Decorative skirting blocked access to critical cam boxes. What looked stunning at speed became a nightmare in the shop. Eventually, the Pennsylvania Railroad cut away Raymond Loewy's elegant streamlining simply to reach the machinery. Even then, the complexity remained staggering. In 1947, an attempt was made to address the failures directly. Valves made from higher strength, fatigue-resistant alloys replaced the earlier mild steel components. The change helped, but it did not cure the underlying problem. The duplex design still demanded perfect balance at speeds where perfection was unrealistic. The locomotives did not explode, and there are no documented fatal wrecks tied directly to catastrophic T1 mechanical failure, but the machines consumed themselves piece by piece. In that sense, they were deadly, not to crews or passengers, but to their own longevity. While the T1 struggled, the Pennsylvania Railroad quietly evaluated alternatives. In late 1944, Norfolk and Western's J-Class 610 was tested between Chicago and Crestline. It made the run 12 times, hauling 11 to 15 cars at speeds around 110 miles per hour. The reports praised its reliability and ease of maintenance. It delivered performance without drama. Adopting another railroad's design, however, was unthinkable. Pride and tradition stood in the way. By the time dieselization pushed west of Harrisburg, the T1s were barely 3 years old. That $14 million investment was effectively stranded. The locomotives were reassigned to mail trains and secondary passenger services, roles that did not suit their immense power. Frequent stops wasted their capabilities, and they were unsuited to heavy freight. By 1949, several were withdrawn and stored. By the early 1950s, none remained in regular service. They disappeared from the roster by the end of 1953. Scrapping began in 1951, and by 1956, the last T1 was gone. 52 locomotives vanished after less than a decade of service. No preserved example survived to answer the questions they left behind. For nearly 80 years, historians and enthusiasts have argued over how fast they truly ran. Officially, the Pennsylvania Railroad set the maximum at 120 miles per hour. Unofficially, the Franklin stopwatch timings suggested something far more extreme, possibly reaching 142. There were no publicized dynamometer tests to settle the matter, and no physical locomotive remained to examine. All that exists are recollections, interviews, and fragments of evidence recorded long after the fact. In 2014, an extraordinary effort began to close that gap in history. A nonprofit organization known as the T1 Trust started building a brand new T1 from scratch, using original plans with careful refinements where necessary. The goal was not a museum piece, but a mainline, capable locomotive. The projected cost was $10 million, later reduced to just over $7 million after acquiring a used Pennsylvania Railroad long-haul tender. The project followed methods pioneered by Britain's Peppercorn Class A1 Tornado, blending modern fabrication with historical accuracy. The first tangible piece appeared in April 2014, a keystone-shaped number plate. A small driving spring link pin followed that October. By March 2019, major components were complete, including 2 boxpark drivers, the prow, the cab, the third course of the boiler, and the fire door. Work on the front tube sheet was underway in St. Louis. Piece by piece, the outline of a legend returned. Whether the extreme speed claims were fact or railroad folklore remains unresolved, but for the first time in generations, there is a path toward answers grounded in steel, rather than memory. When T1, number 5550, finally turns a wheel under its own power, the question that has haunted this locomotive since the 1940s may at last find clarity.